All right, hello everyone, and welcome to our webinar on 5G NR field measurements, sponsored by Keysight's Nemo wireless network solution. Today, we will have a look at what are the challenges of 5G NR field measurements and how to overcome them using proper measurement solutions. Our presenter today will be Deepak Sivakumar, Solution Marketing Manager at Keysight Nemo wireless network solution. To answer any questions online, we'll also have Maddie Pasoja, who's heading the 5G solution marketing at Keysight Nemo Wireless Network Solutions. With that, I give you Deepak Sivakumar.
All right, thanks a lot, Ben. Let me turn on my video. Hi, everyone. I'm Deepak Sivakumar. I manage solution marketing for the North American division for both 5G and IoT. Today's presentation is mainly focused on 5G, though. 5G field measurements in terms of how do you actually go outside and measure a 5G NR measurement, either through a scanner or a UE. And we have a tight agenda, a lot to cover today. Thanks for joining. First of all, we do see 700 plus registrants, so that's very good to know. So in our agenda today, we'll start off by just talking about Keysight and who we are. And then we'll get into more details such as 5G, massive MIMO, and beamforming, and really to set the stage on the fundamentals of all of these technologies, all these technology waves that we're seeing now. We will get into more details on 5G's metrics, some of the layer 1 channels, signals, KPIs as well. We will also talk more about the scanner and device-based measurements and what is available today. And also with 5G, there is a lot of initial testing that is happening right now. So we definitely want to talk about the Pathloss measurements, especially on how we would utilize that for your link budget measurements, link budget calculations, and also propagation model tuning. We will finally wrap up with the roadmap on what Keysight offers today. And if we have enough time, we will also cover questions as well. But yeah, feel free to send your questions as well. There is a lot to cover today. So before I start off though, the presentation that was formed today has been an effort of the entire team. So I want to recognize my team, Maddie Pasoja, Yari Runinen, Yari Skroderis, and Alex Chua, all experts in the field of 5G. So definitely reach out to any of us and we'll be happy to answer any of your questions. Thanks. So a little bit of history on who we are. So Keysight comes, so really the parent company, we were initially formed as HP. That is the grandfather company. And it remained that way, and this was 75 years ago. But a little later on, what formed was Agilent Technologies, which was really the test and measurement division. And it stayed that way for 15 so years. And in 2014, Keysight was launched. Keysight spun off of Agilent, and it became very focused, more focused on the test and measurement division. In parallel, what happened was Nemo was, Nemo Technologies was founded, and that was based on a joint venture between both Nokia and Electrobit. Nokia needed test and measurement equipment, and that's how this joint venture formed. In 2006, Anite acquired Nemo, and in 2015, Keysight acquired Anite. A lot of history in terms of leadership as well, and what Hewlett-Packard and Agilent has brought to the table. So we will get in more in terms of what our specific group does. So we are part of the Nemo wireless network testing division. And again, 20 years of expertise in 3GPP specific technologies. So mainly when it comes to, even back in the day, like, when GSM TDMA was rolled out, we were around. So a lot of experience with, helping build up regular, traditional cellular networks. And really, when you look at the snapshot here, there are different layers. There is the collection, control, and post-processing. So collection is where you would actually collect data on the field. So this is data between the UE and the eNode B. So over-the-air data is collected. All of this data is then, you could control all these devices on the field as well. That's using the control and monitoring piece. And then there is the post-processing layer where you would actually take all of this data and run analytics and have very informed analytics after that. And really, our customers are spread across the mobile ecosystem. So, so everyone in the wireless ecosystem really. So the mobile network operators, we have the network equipment manufacturers, chipset vendors, and then the regulators, and also the services companies who work with all these mobile operators. So really, a lot of experience coming with what we've done on the field as well. And now we've reached the point where we have to talk about, there's so much we are doing with 5G, Keysight especially, and really Keysight, we have been investing a lot in 5G, not just today, but earlier on, while the market was still in the development stages. So really in 2010 to 2015 is when a lot of the research related really started happening for 5G, and Keysight was invested earlier on during those initial research phases. And then 2016 onwards is when we started seeing all of the prototyping, the pre-trials that are happening today in the market. So what that has done is we have been working with all the components, chipset providers very early on with the Qualcomms, Intel, Samsungs. So we have now moved to this phase where we are now in the prototype, and that has helped us move very smoothly with our customer to this phase. And eventually what will happen is, 2019 onwards, we will start seeing a lot of commercialization of 5G. And that's where, when I say commercialization, it's going to be rapid commercialization. So we are very uniquely, positioned in 5G for that rapid commercialization, which is set to occur in the coming years. But yeah, we do have, the solution set that we offer. It is spread across the entire protocol stack, layer 1 all the way to layer 7. And that's why we mentioned field to lab and RAN to core as well. Okay. All right, so this slide talks more about what we do today. And Keysight has made some very strategic acquisitions over the last 3 years, I would say. So what you see in red, the red part represents Keysight Classic, very focused on layer 1 RF type of measurements, really helping chipset manufacturers bring their products to the market, help them build their own chipsets. Also, Keysight Classic is in the device test business as well, with 3G and 4G days, really helping these chipset manufacturers come to market. In gray, what we have is the Nemo group, and the Nemo group, it is mainly focused on device, device drive testing. So this is on field, back in the labs, or there are so many field test cases that can be done on the field. This is mainly between the UE and the eNote B. But there are different flavors. There is also the quality of experience testing, where you could actually run an application like Facebook or Instagram or LinkedIn, which has an API connected to our application, the Nemo application. So you can really measure the user's real quality of experience. There is also another division, the channel emulation, which is a specific group where they do more of they can actually mimic a signal in real world conditions, and you can actually measure what the signal looks like. The one in yellow that you see is the acquisition of Ixia that happened in 2017. So with Ixia as well, now you have, our customers have access to and visibility into, the higher layers. So real network visibility, both for pre-deployment and also, visibility when it comes to post-deployment as well of the network. So really going across the stack, layer 1 all the way up to layer 7, one vendor that provides you with all of these functionalities. And there's a lot that Keysight has done. Mainly we spoke about our engagements with chipset providers earlier on, 2010 onwards. And what that has really done is we've been able to actually do a lot of public proof points and prove really that millimeter wave can be commercialized, really to prove up the physics of millimeter wave. And that's something that we did at MWC as well earlier on this year, where with Qualcomm we showcased that at millimeter wave frequencies you could see up to 400 gigabits per second. We did similar things with Verizon as well. I'm sorry, on the Verizon TF standard as well. There were engagements where and this was pre 5G. But what that allows us to do is there was a lot that we learned over the air testing, link budget calculation. So that allows us to carry all of that information, all of that learning into 5G NR as that is evolving in the coming days. With Intel, we did showcase the world's first 5G tablet-based solution, and with that we saw excellent high speeds as well. So very earlier on, we were engaged with a lot of these consortiums, and the contribution from Keysight. The one significant difference between us and a lot of our competitors in this space is that we have really not been waiting for the standards to arrive. Instead, we've been enabling a lot of these standards to happen a lot faster, working with these chipset providers and our other customers in the market. So let's get into an overview of 5G as well. A lot to cover today. So this is what we've seen in terms of timing and commercial rollouts. Really started with the fixed wireless broadband use case, and deployment in the 28, testing of the 28 gigahertz higher frequency millimeter wave frequency. Excuse me. And then going into both non-standalone, what we will start seeing is both non-standalone and standalone deployments, especially in the 3.5 gigahertz, mainly outside the US. We see a lot more of the 3.5 gigahertz, but within the US, mostly millimeter wave frequencies, but also full mobility between 5G and LTE. And that we will start seeing as we as we see our customers trial the non-standalone mode. But going into 2020 and further on, what we will start seeing is more of the IoT use cases materialize. There is the V2X, which is the vehicle to infrastructure or vehicle to vehicle use cases. Those will start materializing. And then really, going further into the future, we will start seeing these massive IoT use cases. Mainly IoT use cases that maybe the IoT use cases that NB-IoT and Cat-M1 cannot otherwise do. So there's no real rush for the massive IoT use cases, especially since NB-IoT and Cat-M1 satisfies most of it today. But as the requirement for millisecond latency and more bandwidth requirements increase, at that point we'll see those use cases happen. All right, so let's talk about millimeter wave challenge. So a lot of the 5G frequencies, they are being deployed. The plan for a lot of the operators is to deploy on millimeter wave frequencies, the higher frequencies. And really the link budget, when you compare a 5G millimeter wave link budget, it is very different from what we see with the sub-6 gigahertz link budget. Especially if you were to compare, say, a 28 gigahertz, if you were to compare that with a 2.6 gigahertz frequency, you would see that it almost has 20 dB more attenuation than 2.6 gigahertz. The same thing, if you were to compare 28 gigahertz with, say, 900 megahertz, it almost has, the 28 gigahertz has almost 30 dB more attenuation compared to the 900 megahertz channel. 900 megahertz frequency, sorry. So now add to that a lot of the other losses that we see, like rain fade, shadowing, foliage, building losses, Fresnel blockage. That's another key aspect as well, especially with the Fresnel zone in play. And the Fresnel zone is really the radius, between the transmit path of the signal, transmit part of the zone of the signal. If that zone were to be blocked, at that point the signal is lost completely. But if that zone was partially blocked, you would still have an attenuated signal. So a lot of complexity when it comes to test and measure millimeter wave frequencies, and those are some of the things that we will talk about today. So some architectural concepts in terms of standalone and non-standalone modes, and you'll see operators actually go out and test. Some operators who are across different countries might go out and test both SA and NSA during their pre-trials. But really, standalone is where we eventually want to be with 5G. But in the interim, we do have the non-standalone mode, and there are significant differences. With standalone, it is a purely 5G play. Your UE is connecting to your the next generation core to the G node B. Whereas with non-standalone, you still have the UE connecting both to LTE and 5G. So all of the control signaling still happens across LTE, whereas the 5G, the 5G connect is mainly used as a data plane, as a user plane for the data. In LTE, if you remember, really how it was set up was the UE would connect to the E node B to the evolved packet core. So with non-standalone, the evolved packet core is still going to be around for a while. So the evolved packet core is not going away anytime soon. It will still be around, but we will start seeing a lot of the operators, and this is just from what we have heard in the industry. We will see the operators start upgrading their existing 4G LTE systems to 5G, but then it would be through a non-standalone mode, because a lot of the suppliers as well have a very smooth transition plan into non-standalone deployments. But a lot of the operators are very interested in leveraging the existing LTE network, so we will still see EPC for some time around. So let's talk about 5G, massive MIMO, and beamforming, and I'll go through some of the fundamentals that is required for the 5G air interface. So really, to compare, before I get into this though, with LTE, what we have seen is that the channel bandwidth range from 1.4 megahertz to 20 megahertz. The resource blocks are still the same, 12 resource blocks, but you would still have, your subcarrier spacing still remain the same. You have 15 kilohertz of subcarrier spacing. But with 5G, if you look at this, what happens is you have multiple different subcarrier spacing. You have 15 kilohertz, 30, 60, and 120 kilohertz of subcarrier spacing. So what we mean by flexible numerology is, it is just a way to describe the different combinations of that subcarrier spacing and the different slots, symbol lengths. So there are still 14 OFDM symbols in each slot, and you can see that as the subcarrier spacing keeps increasing, the time slot of each of these OFDM symbols reduces. So it's still 14 OFDM symbols, but the slot keeps reducing as it goes, as the frequency, as the subcarrier spacing keeps increasing. And the reason why we have this numerology is mainly because of with the diverse spectrum requirements in 5G, you will have a lot more use cases defined. Ones with high throughput, and we've listed some down here. Ones that have really high latency, low throughputs, high throughputs. So, for instance, the one with macro, the outdoor macro, 700 megahertz, that could do with 15 kilohertz, and the bandwidth could be anywhere between 1.4 and 20 megahertz channel. Whereas when you go to when you take an example of an indoor small cell, and if you were to deploy 5G on between 3 and 5 gigahertz, at that point, you would use a subcarrier spacing of 30 kilohertz. Now, go a little higher into the 28 gigahertz, the millimeter wave frequency, and at that point, the subcarrier spacing is close to 120 kilohertz, but you still have 400 megahertz of bandwidth available. A lot of bandwidth available to transmit at that point. Here's a snapshot of the initial axis, mainly in terms of 5G initial axis, and really there will be a shift in thinking as well. Currently we think about cell coverage, but with 5G, the concept of cell is fading, and it is mainly beam forming, beam coverage that we start looking at. And so with this, you can see there is the G node B. It's a ladder diagram of the G node B and the UE, or the terminal. So initially with the beam sweeping procedure, there are SS blocks that are transmitted. With that SS blocks, those are synchronization signal blocks. There are PSS, primary sync, secondary sync, and the PBCH, which is the broadcast channels that are actually transmitted. So you really think of beams that are transmitted in the air, and there is some minimum system information that is transmitted as well, along with the PBCH. But the UE at that point sees all of these beams, and once it locks on, once it picks the beam, it responds back to the G node B. It sends a RAS request back to the G node B on the same channel if channel reciprocity holds. So the whole concept of channel reciprocity comes in here. If there is no channel reciprocity, at that point, the UE creates its own beam. UE creates its own set of beams back to the G node B, and the G node B at this point knows exactly what the channel information looks like and sends a RAS response back to the UE. Okay. Along with the channel information, along with the RAS response, there is also more detailed system information, RRC connection setup. But at least, and in terms of data, there is a separate beam that is also formed, and that's the PDSCH DMRS beam, the demodulation received signal beam that is also created from the G node B back to the UE. So a lot of different signals that are seen here. We will also, one of the things that, test and measurement companies such as ourselves, we will do is, we will have a lot of KPIs around these beams as well. So in order for you to actually see what that RAS delay looks like, how quickly does the UE lock onto a specific beam? So a lot of different KPIs will be coming up as well. But with this, the main point is you can see that from a really wide beam, starting with a wide beam from the G node B, it then narrows down into a very targeted beam to that specific UE. Which is what would happen with 5G. So here are KPIs that we measure with scanner today, that can be measured by scanners today. And these are KPIs that we measure today. So really the beam index, those are important KPIs that we pick up on today. The KPIs that we would see coming up very soon are the other KPIs, the other signals. And these will be available once the UEs are out in the market. We are still waiting for UEs just like everyone else. But once the UEs hit the markets, the 5G NR devices, we will start seeing these KPIs as well, these signals as well. Because it is not enough that you measure everything with the scanner alone. In order to experience what the UE, what the user is experiencing, and to optimize all of these beams from a G node B perspective, it's very important to test it out with a UE terminal as well. And I'll skim across some of these slides, but this one is just meant to give you more information. These sync signals are, they get transmitted in 5 millisecond bursts. It happens in a total of 20 milliseconds. From a UE point of view, it has to identify whichever is the best beam. There is also something called a time index that comes with every SS block. And once the UE transmits it back to the G node B in the RAS request, the G node B at that point knows not to send any more SS blocks to that specific UE. And as the frequencies increase, the number of SS blocks increase as well. So you can see that under 3 gigahertz, it's a total of 4 SS blocks of beams. But as it increases in the millimeter wave frequencies, we have total of 64 SSBs at that point. So one correlation is that as the frequency increases, the likelihood of beam forming also increases. You will start seeing a lot of beam forming patterns at that point as well because of a lot more spatial directions. Here's a simulation of massive MIMO, and it's a very important concept as well, massive MIMO, as we move into 5G, as one of the enablers of 5G as well. And massive MIMO, really, there are no set standards yet, but it's mainly based on industry momentum. What we've seen that a lot of the findings. But here's a simulation that talks about that shows you exactly what beamforming does in massive MIMO. So in this case, there is no multipath, no obstacles. It was completely done in free space, and we had a 50 omni antenna array, an array of 50 omni antennas. And there are 4 UEs that are strategically placed in different locations. And what we did was we transmitted the same signals at the same time, at the same frequency. And all of this was happening at the same time. But we did capture what that UE experience was across each one of the UEs. So the first one that you see here is, you can see that the target UE, very close to the base station, gets a radiated signal, gets a very strong signal, whereas the other UEs that are further away do not have a signal. It's in dark blue, which means no signal. So we're calling it as the target UE versus the victim UEs or the hollow UEs at that point. Now go back here. So take the next one, for example, the next UE is further away, and you can see that there is a more radiated beam, a more targeted beam towards the second UE at this point. But the other UEs right now are sitting in null, which means that the signal strength was actually minimized going to the other UEs and was targeted only for the UE that needed a beam that had to be formed. The same thing happens for the other UEs as well. For UE3, you can see that it's in light blue, which means it has a targeted beam, whereas the other UEs, the signal going to the other UEs are minimized. So this whole concept of minimizing the signal, targeting the other beams that do need a signal. This is the concept of null steering or zero forcing, and we'll see this in beamforming as well. The fourth UE here that you see, there is more. This is further away from the base station, and you can see there's a more targeted signal, whereas the other UEs are sitting in null at this point. No signals going to the other ones. So really, this test was done in TDD. So channel reciprocity holds. So the G node B really knows. The G node B knows exactly what the UEs are experiencing or what the channel state looks like. If it was FTD, in that case, it would be sent across another channel, because with TDD, both the downlink and uplink goes across the same channel. That's why channel reciprocity is used in this specific test that we did. And this, what you're looking at, is called digital beamforming, where a baseband is used before the beams are transmitted. And this is used in LTE Advanced Pro with transmission mode 9 and also used in 5G. Here's another use case. Here's another test, but this is a more realistic test, we would say, where we actually had obstacles in the path of the UE. So you can see out here that UE is out here. Not sure if you see where I'm pointing to, but there is a target UE, which is behind a corner. But we did have obstacles in the path of this target UE. But you do see that the beam, the G node B still was intelligent enough to transmit a beam, which was then received by the target UE. So the light blue means it did receive a higher signal, whereas the UEs that were closer to the base station were in null. That is minimized. It had a minimized signal at that point. In this case, it does not really look like beamforming. It looks more like scattering in this case. But in reality, this is digital beamforming. This is what digital beamforming looks like in the real world. But this is a simulation, as you can tell. And we do have some definitions of what beamforming is, but really using all of these multiple antennas to sort of control the direction and phase shift, before it arrives at the target UE. That's what beamforming is all about. And there are different types: digital, analog, hybrid beamforming. And depending on the use case, the operator would decide which to use. With LTE massive MIMO, and that's what we're seeing in the market today. It is really a cell capacity feature for the sub-6 gigahertz. And really to achieve, in order to see a lot of these throughputs, especially on the cell side, it is very important to have all of these UEs, simultaneously downloading data, downloading a lot of data. And it's very important that these are also, spatially separated. They're not sitting at the same location. Instead, they are spatially separated. And it's also very important for the user to turn up and turn down these devices as they please, especially if you wanted to see if, adding a new antenna array, a 64T, 64R antenna array to an existing system really made a difference or not. So that's why we talk about the different variables. Very important to know the distribution of users in the cell. either horizontally placed, users placed every 10 meters apart, you could do a test, or you could do vertical testing as well. So both elevation and azimuth testing. There is also multipath radio environment testing. So, that's where you would have users in both line of sight and non-line of sight placed when you do a test. And these are tests that we have actually done, and we've seen the actual field results that we would like to share with you as well. So here's the solution that we have actually worked very closely with customers and have done some of this testing. So here's Nemo Handy, which are the which are the UEs or the terminals that will be otherwise strategically placed in different locations. You could be drive testing, or you could be stationary, line of sight, non-line of sight, horizontally placed or vertically placed. But all of these UEs can be controlled using Nemo Cloud, which would automatically, you could push scripts into all of these devices, which would then turn up and then start collecting data. So depending on whatever TM mode it is, right? If it's TM8 or TM9, it would collect data and then push the data into any of our post-processing solutions. So we do have Nemo Windcatcher, Nemo Synergy, Nemo Analyze, different flavors of post-processing as well. And depending on the degree of automation that you are looking at, we can automate all of these functionalities. And here's a snapshot of what and some of the testing that we did out in Oulu. Here's some of the test results. So you can see that in the first snapshot here, we have total cell throughput. So this is the total aggregated throughput that the site was pumping. So because at the end of the day, it is a capacity feature, and it is not enough that the UEs get good throughputs. It is also very important that you push a lot of data through those massive MIMO cells. So there is the total cell throughput that's displayed here, and down here there is also throughputs per UE. So if you have multiple UEs on the field, you would also see UE throughputs per UE shown as well, like what we're showing you right now. It's also very important to see where these devices are. So you would also have a visual, view of all the devices. If you're drive testing, you would see that. But if they're stationary, and you can see in this case the antenna is here, but you have all your UEs that are separated. And we had a bunch of users standing here, walk testing, and then we had some that was stationary in this. So a lot of KPIs we will start seeing. And some of the KPIs, just to go over what we've seen with 5G, layer 1 channels and signals. On the downlink, we spoke about the SS blocks, the PSS, SSS, and PBCH. Those will be available with the scanners. But Nemo also will have the ability to see the UE-based measurements once the terminals hit the market. So that's where you will start seeing your CSIRS, your channel state information, your PDSCH, PDCCH. On the uplinks, there are their own set of signals, and these can be seen only using the UE. So you will start seeing your PRATCH, your RATCH response signals, your SRS, your sounding reference signals on the uplink at this point. So here are some other KPIs. The one we earlier saw was signals, but these are KPIs. So we will start seeing sync blocks, and then the primary sync channel, power, quality, and SINAR. So that is the RSRP, RSRQ, and SINAR specific. From a UE standpoint, it's going to be a broader list, a bigger list. But these are the KPIs that we will start seeing very soon once the devices start collecting. And you can tell, RSRP still comes from 4G, but then these are more of, primary sync RSRP, secondary sync RSRP channels, signals. All right, so let's talk about, I think, it's a good place to transition into what we have seen in the market. And we are very excited to show you the first snapshots of an actual signal being captured by Nemo Outdoor. This was done using Nemo Outdoor and a third-party scanner. And you can see that in this snapshot, we are showing you an actual signal that was captured by Nemo Outdoor, and we also show you all the beams that we've seen. So this was done in a lab setup. That's why most of the beams are very, that's why the signals are so good. but it was an actual signal that was transmitted. So if you look at this, it says it was 5G NR band 77, and on the right side here, there are different windows. There is your RSRP, SINR, RSRQ, RSSI, but what you would also see in here is the RSRP per beam, and that's what we show here. There's something called a BI, or a beam index, and we are showing you all of the beams that are listed in here, along with the RSRP per beam. Like I was saying, in a lab situation, the signals are really, they're extremely good signals. So that's why everything is, it's dancing around -70. But in real life, in a real field condition, these signals would be all over the place, especially with beamforming and users being in different locations. We would see this, we would see a different chart at that point. But at least we wanted to share this snapshot with you on what we have done in terms of testing today. And the reason why we've been able to do this very early on in the market is because we do have, that relationship. Well, we are now under the same Keysight umbrella. So with the Keysight Classic folks, there are the UXM, the devices that actually transmit these 5G NR signals, actual signals that are transmitted, which can then be captured using our scanners and outdoor platform, which can then decrypt that signal and actually show you the demodulated signal. So this is in terms of a demodulated signal, which would come to the market eventually, but available on Nemo Outdoor today. But what is happening today? What we see a lot happening is the CW testing. So that's the continuous wave testing that is happening in the market today. So this is mainly used for the earlier on link budget calculations, path loss measurements, especially especially for engineers such as yourself in their propagation model tuning stages earlier on. Because it's very important to do this link budget estimations very earlier on to estimate the number of G-Node B sites that are actually needed for deployment, and also it is important to measure it both on the uplink and downlink, especially because going into millimeter wave frequencies, we spoke about the challenges of millimeter wave frequencies. The higher we go into this millimeter wave frequencies, the narrower the Fresnel zone is. So the blockage is also going to be a lot more at that point. So very important to test out path loss measurements. Similarly, so what you see here is the actual, so Keysight's FieldFox scanner. That's the one I'm pointing to, the FieldFox scanner, which can be used as a transmitter to transmit one of these 5G NR signals. So on the higher frequency, so you can either transmit it using FieldFox, and on the receiver side, you could have FieldFox either with an Omni antenna or with a rifle scope, in this case, what you see, with the horn antenna actually receiving the signal. And in this case, you would also see that FieldFox is connected to Nemo Outdoor, where you can actually see all the collected data. Okay? And all of this data can also be post-processed in any of our post-processing tools. The other option is you just receive it from a G-Node B directly, and you still do your CW testing. You either drive around or you do a walk test in a building. Okay, all right. And a lot of these measurements can then be brought directly into your propagation tools. So Nemo being around for 20+ years, we are compliant with a lot of the tools out there. The file format is the smallest in the market today. So we do provide the smallest file format, and you could, and a lot of the propagation tools out there in the market would consume that file directly, since we already work with a lot of the propagation tools. Here's a snapshot of a signal. This was transmitted on 28 gigahertz. The channel goes between 27,825 all the way to 27,730 megahertz. But this is just to show you a waterfall chart on a history of what that specific signal looks like. Areas where I have the signal. So across the frequency, you can see what the signal where you do have good signals. But if you wanted to see it across time as well, you could do that as well. So down here is another chart with just the frequency, with the time. time series and the signals, the RSSI signal. So there's a lot that we've been doing, working very closely with the chipset providers, and we wanted to sort of share our roadmap with you as well on what we are doing today in the market and what is available today. So in this case, currently what is released is the ability to measure 5G CW testing and actually perform a lot of this CW testing on the field, especially to see all your RSSI measurements. And we are the only vendor out there today with FieldFox and Nemo Outdoor that does CW testing, going up to 50 gigahertz, going up to 100 gigahertz with the down converter as well. Mainly for path loss measurements, link budget calculations, and also a lot of the propagation model tuning. We are also very involved with helping customers with LTE advanced 5-component carriers, 4x4 MIMO, 256 QAM. There is also LTE flavors, so there is the license assisted access. And in terms of CBRS, we are now part of the CBRS Alliance, actively involved in a lot of the discussions. Definitely, when it comes to CBRS, and there's a lot more, technology waves coming, like multi-fire, very involved with a lot of those as well. There is also, so once all of this data is captured though, they can be post-processed. So in order to see that we have UIs or the user interface created just for all of these different UIs. And in 3Q 2018, what was released is we do have scanner support for 3G PPNR. So that's the snapshot that I showed you with all the beam related information, beam index, RSRP per beam. All of that information is now captured. We will still keep adding more and more metrics as available, but we wanted to share that snapshot with you because earlier on, a lot of this, lab testing requires, a scanner measurement tool that needs to be available. With LTE Massive MIMO, we showed you some snapshots on what that looks like in the market, on how you could actually test Massive MIMO, command different devices to turn up, turn off, and send data into a post-processing tool to automatically post-process and create really nice fancy reports, which you can then turn around and provide to your end customers, whoever that is. If it is a services company, if you're a services company, we do have operator, very operator-specific reports for Massive MIMO that you could turn around and provide back to your operator. In 4Q, later this year, what we will have is support for scanners up to 39 gigahertz as well. There will be 5G and LTE multi-mode connectivity analysis and more detailed analytics for 5G and scanners as well. 2019, early 2019, what we will have is support for the Qualcomm X50 chipset. And very earlier on, like what I was saying earlier on, is that we are working very closely with Qualcomm in the labs. Qualcomm is actually using Keysight's UXM product in order to build the X50 chipset, and we did showcase 400 gigabits per second throughputs. But this relationship is now leveraged, and what we will have is we will have these chipsets. We will have the ICDs later on this year in 2018. But once we have the ICDs, we will have support for the X50 chipset as well in our handy collection platforms and outdoor as well. Along with Qualcomm, we will have support coming up, and some of these dates, like the one I have for 2019, 2Q with Samsung and HiSilicon, it is the Exynos chipset and the HiSilicon chipsets will be supported as well. But we are dependent a lot on these third-party vendors. But we are working, needless to say, we are working very closely with them and aligning our roadmaps with theirs as well, and our operator customers' roadmaps. So we do have some time for questions, but before we get into questions, just to summarize what we spoke about, there is a gradual evolution into 5G NR and the availability of 5G chipsets and UA equipments. We are actually waiting along with you for these 5G chipsets to be released. But we have done a lot of testing. We are working with some of our customers very closely. And as these devices are available, our collection tools will have the availability on our collection tools. So for our customers, it will be a very easy plug and play approach once the devices arrive to the market. But what we have done in the meantime is be very prepared, and we do have solutions for CW testing for 5G NR frequencies, especially the higher frequencies. So if it was a model tuning use case or a band clearance, excuse me, or interference tests. So if you had frequencies that you bought off an auction that you wanted to test and see how it performed, you could actually use our CW testing package in that case. We do support the scanners. We do support third-party scanners for demodulation in some cases. So you could actually see all your beam-related information. And with 5G NR, the UEs, it's very important to not only see the scanners, but also understand from a UE perspective on how the terminals are performing. So there will be a broader range of KPIs at that point. And with Keysight Nemo Outdoor, we support all the major current use cases that are possible in the market today. So definitely, we did have a paper on beamforming that was recently put out as well. So I would encourage everyone here to check out some of our beamforming massive MIMO articles as well. But thanks for joining, everyone. I think we do have time for questions as well. So let me take a look at the questions at this point. But yeah, go ahead, Ben, if there are any questions that you've seen as well.
Yeah, sure. Thank you so much for your presentation. So I'm going to ask you just a few questions, and if you see any from the audience as well that you would be interested, please go ahead and answer those. But I would like to know, do you support all 5G scanners?
We do support all the major 5G scanners that are in the market. All the all the big scanner major companies. We definitely support them. And one of the snapshots that I did show you was a snapshot with outdoor actually collecting all of that beam information. So we are working more closely with some of the other vendors as well. But as it evolves, if you have a specific requirement for a 5G scanner measurement, definitely reach out to us. But yes, we do support all the major vendors today. Yes.
Great. When will you be able to perform measurements with UEs?
So with the UEs, we are dependent on the chipset providers as well. So as the terminals are available in the market, that's when we would support it as well. But we do have, but due to our relationships with a lot of the chipset manufacturers very earlier on during the research phases, we have been able to understand a lot of the KPIs. So when the devices are available, most of our customers will have support, or at least a software patch, a version available. So they would be able to start measuring once the UEs are available.
Awesome. And one last question, for field measurement and optimization, what's the biggest change in 5G compared with 4G?
So for field measurements, with 5G, well, let me start with 4G. With 4G, the whole concept of measurements was around, cells, with cell coverage. But with 5G, there's going to be a paradigm shift. Mainly the measurements are going to be more focused on beam coverage. And that's why we covered a lot specifically to beam coverage measurements, understanding both your synchronization channels, both your PSS, SSS, and your PBCH in terms of your sync blocks, especially because you would have all of these beams radiated. It's very important for the UE to pick the right beam, and then, and after that, the RAS procedure happens. But a lot of the engineers, a lot of the folks in the field would start looking at this mainly from a beam perspective instead of a cell perspective at this point. Okay. Okay, there's one question here. Are there measurements in slide 26 based on 3GPP NR or Verizon TF? So the measurements that we showed you was based on 3GPP NR. So there's another question on channel state information. What is channel state information and how is it actually used in TDD? So with channel, well, not channel state, but channel state and channel reciprocity. So, you know, the channel reciprocity concept is fully based, you know, it's mainly based on the TDD, where, you know, both the uplink and the downlink channels are on the same frequency. Both the uplink and downlink are on the same channel. Whereas on FDD, you would have uplink on one channel, whereas DL on the other channel. So with channel reciprocity, once the UE actually picks up on, you know, once it picks the beam, from a UE point of view, it responds back on the same channel and on the same uplink channel back to the G node B. And that is only if it is a TDD system. If it was an FDD system, I mean, what we're seeing is that the UE would, at that point, create its own beams, which the G node B would then pick up and do a ratchet response back to the UE. Can we get the slides? Absolutely. We will definitely share the slides with you. So is 5G NR a completely new technology or an update of LTE? So, so NR mainly a lot of the you know, a lot of the concept is inherited from LTE, but there are also a lot of new things in 5G, especially with the 5G numerology that we spoke about, the scalable and the flexible numerology that we spoke about. Especially with the subcarrier spacing, it goes all the way to 120 kilohertz, whereas with LTE it was only a 15 kilohertz subcarrier spacing. And this is mainly so that it is a more diverse spectrum, and there you will see more use cases materialize with 5G as well. Especially you will start seeing massive IoT use cases as well come up. Okay, when it comes to 5G standalone, is there a standard architecture being deployed similar to LTE core network? So with 5G standalone, the core network is still standardized in 3GPP, just like in LTE, but there will be different options in implementation, especially with with standalone and non-standalone. Within the non-standalone mode itself, there would be different combinations of how the UE actually talks to the EPC, talking talking to the NGC, to the next generation core. So there will be different combinations even within the non-standalone mode, and depending on the operator and their specific use case, that is there are a lot of pre-trials that are happening today for them to actually pick whichever is their best route forward. Can this scanner data for CW testing be imported in mmWave? Yes. So a lot of our, today, if you were to do a scanner measurement, or if you were to collect a Nemo file, our Nemo files are very compatible with a lot of the other platforms. So you could either post-process them in other platforms, or you could also do an export in order to import it into other third-party software. So we do work really nice with a lot of the other softwares out there as well. So definitely, try that out when that happens. Will this be used for walk testing as well? There will be walk test cases, walk testing use cases as well, especially if you're inside a building and you wanted to measure what that building loss is, and along with all the other losses that are involved. At that point, for CW testing, you could still have the FieldFox connected to Nemo outdoor. You could draw pinpoints on the map while you're walking inside a venue or a building or a casino, wherever it is. But in this case, you would have an Omni antenna on top collecting data, which you can then post-process in our post-processing platforms and see what that looks like on a map. So there is a question about intra-cell interference, especially with beamforming. So with beamforming, one of the main objectives is to have these grid of beams. The whole concept of grid of beams, or GOB, where you would have initially a lot of these beams actually formed during the beamforming initial procedure. And the main objective is, once the UE picks up on a beam, that beam is not meant to interfere with any of the other beams. So there shouldn't be any intra-cell interference. During beamforming. Now, of course, with beamforming, it is a complex topic. There are a whole list of beam management related KPIs. So especially with beam management, there's beam determination, beam steering, beamforming, a lot of other KPIs that we will start seeing around beamforming as well. There is a question on massive MIMO. Will it be with 64T, 64R? From what we have seen in the market, massive MIMO, some of the testing that we did recently, it was a 64T, 64R system. But it was mainly an implementation of the network equipment manufacturer as well. So I think that will change depending on the network equipment manufacturer, whatever the frequency band that is being utilized, and also and based on that we will start seeing different transmission modes as well, whether it is the TM8 or a transmission mode 9, we will start seeing that as well. Is 5G NR carrier aggregation testing available? I think a lot of the 5G NR carrier ag testing, it will be available once the UEs hit the market. From what we have seen, from what we've understood, it looks like at times you could have a 4G LTE. Especially in a non-standalone mode, you could have carrier aggregation along with 5G, really to fatten that pipe. So some of that testing will happen as well in the days to come once the devices arrive. Will demodulation measurements be available in the 5G scanner? Absolutely. The snapshot that we showed you was with demodulation. And what will happen is you will also have availability along for the other scanners as well. But we do have demodulation available if that is of interest. But for CW testing, there is no demodulation required. But as an overall, once the devices are available, there will be both UEs. It will be a blend of both UEs and scanners, scanner testing in the market to really measure that 5G signal. I think we are on the top of the hour. Is there, Ben, back to you, but thanks a lot, everyone. Thanks for joining.
Yeah, thank you so much, Deepak, and thank you everyone for joining us today. I really appreciate your time, and we look forward to speaking with you again another time. Any questions that were unanswered, we will be happy to have the team go back and answer. And yes, the recording will be available as well as the slides to everyone. Once again, thank you all so much for your time and have a great rest of your day.
Thanks a lot, everyone.